We're going to talk about minimums and maximums of quadratic functions, quadratic equations from this standard format, right? Ax squared plus bx plus c. We're going to go ahead and investigate what the highest y value is or what the lowest y value is, depending if it opens up or if it opens down, the parabola is. Right? So there's an open up parabola. There's a open down parabola. So you'll notice that on the open up, you have the lowest possible y values here. I'm going to explain that about 3 or 4 times here. But on the one that opens downward, you have a maximum point. In other words, there's a highest point for y that you can reach on this graph, and you can't go any higher than that. So let's talk about x. X is the value that you plug into the function, okay? I always thought a function could have been like a circus cannon, where x is what goes in the cannon. Right? Pretend we stuck in -1 into this function, and we would simply solve. Every time we saw an x, we'd substitute it with -1, and we'd get some final answer. Okay? And these are all the values of the x that you can pick from. Right? Any x value on this x-axis we can pick from. So this leads right into the domain of this parabola. So the domains of all parabolas, believe it or not, is all the numbers on the number line. We can use any x value for this function and plug it in anywhere at all times. So that is a truism of all parabolas. You can stick any x value in there that you want. So the domains of all parabolas is the entire real number line. So that's half of the Cartesian plane. Let's talk about the other half, okay, the up and down half. I don't think half is the right word, but direction. Direction would be a better word. So now we're going to talk about the f of x, not just the x, the f of x. Also called y, right? Y is a different number than the x, but the f of x and y can be interpreted as the exact same thing. But it's this side, it's whatever this number is, after you do all the math and all the calculations, after you plug in the value for x. Okay, and that's any number on this axis. It's another real number axis, real number line, but it's just vertical instead of horizontal. But one very important thing with parabolas, their y values stop pretty soon because of the graph. That your y values cannot be reached. Let me try to show you that with a picture here. So with this example right here, the very highest y value you're going to get is whatever that point is right there. You will never get a point on the graph that's higher than whatever that point is, right? Let's talk about the ranges of a parabola. A little bit different than the domains. A range is what comes out of a function, but with parabolas you're restricted. So the range of all parabolas is y can be any number on the real number line, except for it has to be less than or equal to the maximum or the minimum of that function. In truth, there's a whole lot going on here. This is called graph theory, but if you can grasp this idea firmly between the graphing and the mathematical connotations there, that's a big chunk of the mathematics, especially with quadratic equations. So let me try to show you this. So the x, you could pick any value for x, right? And you plug it into the little cannon, and the cannon shoots it up to wherever the y is. And we know where the y is because it's dotted on the graph, okay? So these points on this parabola basically were calculated from whatever the formula was. Okay, so any x can go in, and after you do the calculations, any y will come out. You put parentheses around them, and this becomes our coordinate system. The x is what goes in, it's called the abscissa. The y is what comes out, that's called the ordinate. So let's go ahead and remember, you can take any x value for the domain for any parabola. But now, if I pick this x value, whatever it is, I know what the y value is because the graph tells me so. Okay, so when I pick that x, it's going to go ahead and pick that point, and that point has a y value of wherever it crosses the y-axis, that straight line. So in other words, this value of x will generate that value of y, and that point will be on the graph somewhere. So that could be one of the solutions here for a different x and y. But now we're going to talk about two specific points. We're going to be talking about the very highest point we can get on the y-axis. That is what we call, the greatest y value is what we call the maximum. And we're only talking about the y value here. For minimums and maximums, we're only talking about the y-axis. Okay, so the maximum is the highest y value you can attain from a parabola. And for our example, it would be whatever this point is right here. And you would have a specific x that would generate that specific y, which is also the maximum. And the minimums work the same way, but upside downy. Okay, so the minimum is, first of all, the parabola has to open up in order to have a minimum. Remember, with a maximum, the parabola has to open down. So for a minimum, same thing. We're looking for the lowest y value this time. Okay, and no lower values for y could be under the minimum. Okay, so our little example here is whatever that point is on the parabola, the y component of it, the y part of it, would be wherever the smallest value that equation would generate. So remember, a unique x value, only one x value, will generate a minimum y value, and that's what we call the minimum. Okay, so both of those, I hope you noticed, the minimums and the maximums were on the vertex. They were both on the vertex. So to find a minimum or maximum, all you're going to do is take the equation, the formula, and find the vertex. Again, a big hint, when you hear the word minimum or maximum, you're going to find the vertex of that quadratic equation. So let's do a couple. Let's do the maximums first. So here's our problem. We're going to maximize profits based on a quadratic function here. So which price P maximizes revenue R for a company selling textbooks if the revenue function is this? Bam. So make sure you understand the question. Your little individual x value is the price of the book. Okay, that's your little p. When you plug in p, whatever that value is on the other side of the equation, that's going to be your r of p, your f of x accordingly. Okay, so we're trying to figure out what the price should be for the textbook that's going to maximize this company's profits. So there's the equation right there. And what are we going to do? We're going to find that little point on y that is the highest y value we can get, also called the maximum. Okay. Looking for the maximum, looking for the maximum. Looking for that value. That's going to be the total amount of money that's going to be brought in depending on what price for the textbooks we have. Okay. It's your greatest possible y value from this function, which from this problem is the greatest possible revenue. So we're going to find the vertex. Make a big one. So we're going to substitute b to a for the information from the quadratic function up there. Right? B is 16,000 and it's negative. Divided by 2 times negative 100. And I believe that boils down to 80. Good. So now we're going to plug 80 back into the function. So 80 squared times negative 100, whatever that is, plus 16,000 times 80. That's a big number. Let's do some math. I'll do it for you. Comes out to 640,000. Bam. So let's interpret this bad boy. What that literally means is, for price P, the textbook price P of 80 bucks would generate the maximum revenue possible from this function of about $640,000. Say it again. The price of 80 bucks will maximize the revenue for the company at $640,000. Textbooks are not cheap. All right, let's do a minimize example now. Usually you want to minimize your cost, right? You want more money coming in, more revenue, less cost. Question is, how many pencils should be made to minimize the cost if the cost function is the one below, right? X squared minus 6x plus 300. A little sidebar is the x are in units of 1,000. So whatever the x value is when we're finished, we're just simply going to multiply it by 3,000. And the c of x, the y value, is in units of dollars. Okay, we can remember that. We're going to find the vertex. Vertex, vertex, vertex. I love the vertex. So negative b is going to be negative 6 over 2 times a. A is 1, right? And that looks like positive 6 divided by 2. Looks like 3. We're going to plug 3 back into the function. Shkabam. So let me see if I can do this in my head. 3 squared is 9, minus 18 is negative 9. So 300 minus 9 is 291. So interpretation for this guy is x is the total number of pencils, right? And that's in thousands. And y, the 291, is the output, is the c of x, and that's in dollars. It's going to be the minimum cost. So the minimum cost would be about $291 if 3,000 pencils were made. And you want to figure out unit price there. So you're going to divide 3,000 by 291, and it comes out to be about 1 pencil would cost you about $0.097, which is about 9.7 cents, which is about around a little less than a dime a pencil. But that's it. That's how you find minimums and maximums of quadratic equations. MGZ.